So this is going to be a quick tutorial on the law of conservation of energy, where we're going to pick up on our discussion from yesterday on the work energy theorem. I'm going to start immediately with the equations that the work energy theorem we established yesterday, and then we're going to move to the law of conservation of energy with really 3 or 4 examples. So we said yesterday doing work on a system changes the amount of energy in a system. And there's different types of energy. So we can summarize this mathematically as that the work done by a non-conservative force, remember that's any force that doesn't try to bring it back. So it could be friction, it could be, if it's friction it's negative, if it's an applied force it would be positive. That goes to changing the kinetic energy of the system and or the potential energy of the system. And that potential energy could be gravitational, could be elastic. For now we're going to really focus on gravitational. So this would become, if we expand the deltas out, that would be our final kinetic minus the initial kinetic plus our final, let's say, gravitational potential minus our initial gravitational potential. So we see we just have to keep track of what energy we have before and after. And we'll look at that a different way. And then the idea is if you do no more work on a system, whatever energy is in a system remains the same. That's a conservation law. But it can shift from one form to another. So the energy therein, whether it's all potential or kinetic or a combination, will transform. That's a little bit different than momentum. Momentum usually is one type. It can be transferred from one body to another, but there's not different types of momentum that we talk about in that. Okay, so another way of expressing the law of conservation of momentum is simply in terms of totals. So we can say the total energy of the system is equal to the sum of its kinetics plus the sum of its potentials, right? This is mechanical energy now that we're focusing on. So if we expand that out, we can say, all right, let's look at what energy we have at the beginning of an event. So that could be in the form of kinetic. Whoops, that's okay. And I'll put a naught there for 0. It could be gravitational potential. I'll put a naught there. It could be spring potential. All right, so let's say those are the 3 mechanical energies we have to consider at the beginning of an event. They add up to our total energy. Then we're looking at an event some point later. It could be a roller coaster going through a bunch of hills. And we ask what's going on there. Again, we only have to consider what energy or energies it has at that position. So that might be some kinetic energy still, but different amount. It could be gravitational potential energy. It could be some elastic potential energy. So let's combine that in that blank. And then if there is non-conservative force like friction, we might also generate some Q. So I put that in parentheses because some problems it won't be there and other problems it will be. It needs to be made clear. So schematically, what we can do is look at, we're going to look at 2 ways. We're going to look at pie graph and then a bar chart, which is a little bit more involved. So let's take a simple conceptual example of a moving ball rolls down a hill, and then there's 2 cases, no friction and friction. So first of all, work had to be done to give it energy in the first place. And once it's done, we take it away. So we say it, in this case, has 2 forms. Because it's moving, let's say it's kinetic. And then because it's on top of a hill, there is gravitational. We'll assume there's more gravitational and kinetic, but there's nothing in the wording that suggests one or the other in terms of relative amount. And then it goes down a hill. And so if there's no friction in case A, we are still going to have kinetic. It's definitely moving, and we see that it's going to gain kinetic, all right? Why did it gain kinetic energy? Because by going down the hill, its height is lower, so it lost potential. So it's going to have less potential than before, therefore more kinetic. But the whole pie hasn't changed. We just shifted from potential to kinetic. If we roll down a hill and there is friction, it's the same idea, but you notice there's a third chunk of the pie because friction is going to generate Q. So there's going to be some thermal losses, if you will. So notice that the bottom part of this pie hasn't changed compared to the upper part because our potential has got to be the same. We're at the same height regardless of whether there's friction or not. So the potential energy afterwards, when we're at the lower spot, is going to be the same, meaning we have less kinetic than the original situation. But again, they must all add up to the whole. So another way of looking at this is an energy chart. So we'll do a quick example of that without any numbers before we go into the numerical examples. Okay, so we have a block on a ramp. It's being pushed up, and you've got to read very carefully. The block is moving, all right? It's a smooth, frictionless surface, and it's increasing speed from A to B. And we're going to complete this bar chart in a second, but here's what we want to be careful of. It says the Earth block system, so remember, potential energy really occurs between the Earth and the block that's gravitational, not just in the block. It moves from A to B, and it says the height of 0 is when we're at position A. Okay, so that's important. So if we look at this chart, we have a initial, or before, we have a during, in other words, is any work being done, and then we have a final. So we're just going to keep track of the types of energy and then put the relative values and try to be somewhat accurate. Okay, so let's ask yourself, is there any kinetic energy at the beginning of the event? And the answer is yes, it's moving. So let's arbitrarily assign a certain number of bars to that. Okay, since I've worked this out in advance, let's say there are 6 units of energy. 1, 2, 3, 4, 5, 6. So let me just kind of enclose that. All right, is there any potential? Now, if you look at the diagram here, it might look like it is, but remember, we started at A, and A was defined as 0, so there's going to be no gravitational potential at the beginning of the event. There's no springs involved, so we can ignore that. Now we can move on to the during. Was there any work being done on the block? Well, you have to ask yourself, was there an external force? Gravity would not be external here because our system is Earth / the block, but there is that hand pushing, so that is external. Is it positive? Yep, because it's pushing in the same direction as moving. So let's arbitrarily say that there are, let's say, 4 units of work being done on it. Okay, so we're going to fill in the 4 blocks there. So what does that mean? Well, our final energy of the system has to be what we started with plus whatever work we did. So if we have 6 here and we have 4 there, then we have to have a total of 10. Now it's just a question of distribution. Well, Q is going to be 0 because there was no friction, so that's easy. Potential had to go up because we're at a higher place. We don't know how much higher, but we know it's more than we before, so it's either all the 4 or some fraction of the 4. It can't be all the 4 because we saw that it's increasing speed, so there had to be a gain in kinetics. So let's just say of the 4, let's say 3 of it went to potential because it's higher. And therefore, we have to have 7 for the kinetic. So we're going to be 1 bar above where we started. And there we go. We've kept track of our energy. Why would we want to do that? Because ultimately we might ask, well, how fast is it moving? And we can base that on the kinetic energy of the system. So let's look at an example that does such a thing. Okay, so I'm going to alter this a little bit because when I looked at it more closely, a few labels on the left that I didn't like, but not a big deal. Okay, so we got numbers here. We have a 10 kilogram cat launched horizontally at a certain speed from a certain height. And then you're told for each meter it falls, so it's going to be in free fall, it will feel 10 newtons of drag. Okay, that's important. So there's a, if you will, a force of friction. Okay, so complete the energy bar chart for the following. And the goal is, what is the V at the bottom, right? What's V prime when it just before it hits, or excuse me, at a particular height? Okay, so let's do some numbers. So our first situation is we're at a height of 2 meters. Remember, we started at 6. So we want to know what is our energy distribution after we've fallen 4 meters. So the beginning, we want to know how much kinetic energy do we have. Well, we weren't told outright, so we have to calculate it. M1/2 mv naught squared. Okay, you can put in 1/2 of m is 5 times 4 squared. That would give us 80 joules. Okay, so we'll go over to our bar. Let's assume each line is 100, so we're not quite to a full one. See in a second why I chose 100 for that, so I'm going to label this 80. Okay, what's our initial potential energy? Well, that's going to be mg, our initial height. So m is 10 times 10 is 100. Our height was 6, if you read closely, so we have 600 joules of potential. So a lot of potential, not a lot of kinetic. So if I go up 1, 2, 3, 4, 5, 6, okay, I've got 600 units of potential and no spring energy. So that's important. I'm going to put right below here, we've got a total of 680 joules of energy. Now, was any work done on the cat as it was falling? Well, again, gravity wouldn't be an external force, but there is drag. And so drag, when we saw that there's 10 newtons, so the Q generated, okay, is going to be equal to the force times the distance. Since we're at a height of 2 and we start at 6, we've fallen a distance of 4 meters. So that's 40 joules. Now, I labeled this as Q, but this is really the work done by the non-conservative. So that's going to be negative 40 because it was opposing. In other words, the force was up while the displacement was down. So we had a negative amount of work done on the system. So let's label that as negative 40. So the easy mistake to make is to say, well, we took away 40 units from the 680. In one sense we did. We took away 40 units from the system, which was the Earth/cat, and we put it into something else. But we're going to look at this a slightly different way. The total energy still has to add up to 480, but we can look at this negative work done by drag is that it gave us 40 joules of Q. Okay, so that's got to be a positive. You can't have a negative amount of thermal energy. So there's 40. So again, let's make the connection. The work done by drag against the motion went to giving us thermal energy. Okay, so that's going to become important. Now, the next easy thing to look at is what's our new potential energy. So we're at a height of 2, so if we do mg times 2, we can easily deduce that we have 200 units of potential. So what does that leave for kinetic? Well, we can say that the kinetic, and I'm going to do the work out here, prime, is going to be equal to our total, the 680, minus what we have in the other forms, 240. So that's going to leave us with 440 units. So 1, 2, 3, 4, go halfway up, and there's our kinetic. Okay, now we can find the velocity. If we know that Ke equals 1/2 mv squared, then our v prime, if I do the algebra, is going to be twice our kinetic divided by the mass. I'll let you work out that algebra. So we have 2 times 440 divided by 10. And then I'll work out the numbers. Okay, and that's 9.4 meters per second. So now we know how fast it's moving by virtue of how far it's fallen and what work has been done by friction. All right, now in the next example, let's say we're at the bottom just before it hits. How fast is it going? So it's the same issue. We've got 80 joules of this. Nothing's changed. It was initially moving that, and it had started off with a initial potential energy of 600. I don't need to recalculate that. Okay, so 680. So let's change this to U prime, because let's do a calculation of that. And then let's call this W non-conservative, and then we'll do V prime. Okay, so is there any work being done? Yes, it's a force times the distance. Again, the force is 10 newtons, but the distance is 6 meters because we fall in 6 meters, so that's 60 joules, and it's negative because it's going against it, so we're just shading a little part there, negative 60, which means we have 60 joules of thermal generated. Okay, what's our new potential? Well, that's going to be mgy prime. Well, that's going to be 0. Well, that's easy. There's no potential energy. We're at the ground level. So what does that leave for kinetic? That's pretty easy. So we had, again, 680 total. So our 680 minus 60 leaves 620 joules of kinetic. 1, 2, 3, 4, 5, 6. Go a little above there. 620. Now we can calculate the speed again. Square root of twice 620, all divided by 10. You work that out, you get about 11.1 meters per second. Okay, so this is a convenient way of figuring out how much speed you're going. You can't without doing kinematics and laws of motion. Okay, so the last example, might get run out of time here on the thing, is a similar one. We're going to fire a bow up into the air at an angle theta, and we want to know how fast it's going just before it hits the ground. If this is projectile motion, this is kind of a pain, but it's very easy if you look in terms of energy. So what's our total energy at the beginning? Well, it's all going to be kinetic, because it's moving when it leaves the bow, plus some potential, okay, because it's above the ground. Then it comes, and just before it hits the ground, there's still kinetic, more of it, but there's no potential because it's at ground level. So what we can say then is, using conservation of energy, how would we figure out the speed? Well, I take the initial kinetic, 1/2 mv squared, plus mgy is going to equal 1/2 mv prime squared. From over here, since there's no potential, we can now solve for v. And I'll let you do that on your own because I'm out of time. Okay, if you have any questions, bring them into class.